Hello everybody, I'm Sanjeev from Fire Lab, Electrical Engineering Department, Indian Institute of Science, Bangalore. In this video, I'm going to present our paper titled Automatic Identification of Speakers Using Head Gestures in a Narration. This paper is scheduled for oral presentation at ICASSP 2020 in the topic of multimodal processing of language. This is the plan for the entire presentation. First, a brief introduction on what head gesture is, its importance, and research done till now. Next, we'll talk about the data we are using for the experiments. Then we'll discuss our proposed approach in this paper. Moving on from there, we'll talk about the results which we got from the experiments, and finally, the conclusion. Head gestures convey a lot of paralinguistic information. Two well-known head gestures are nod and shake. While nod generally means an agreement, shake on the other hand usually means a disagreement. Ekman et al. Have shown that intensity of speech can be inferred from head gestures. Speech of any kind has been proven to be more comprehensible if it is accompanied by corresponding paralinguistic features like head gestures. Gunes et al. Have shown that head gestures also convey the emotional state of a person. Nonverbal cues have been shown to contain information about personality traits of a person. In a similar research, the head gestures induced in a person while he is subjected to music also were shown to contain information on personality traits. As personality changes from person to person, these works provide evidence to believe head gestures might have person-specific information. Hill and Johnston conducted a subjective experiment to determine how well people can distinguish head gestures of different people. Based on the statistical test, they conclude that speakers can be distinguished based on the head gestures. Some of the applications of head gestures are inferring the emotional state of a person. This can be used in virtual counseling, where the counselor can use the emotional state of the counselee in his counseling. Conversational robots interact better with proper head gestures built into them. Head gesture analysis can also be used in forensics to identify the speaker in case of blurry or masked videos. This is our recording setup. We have 3D tracking device from OptiTrack with 7 infrared cameras. If you observe, this stand has 2 cameras, this has 3, and this stand has 2 more infrared cameras, totaling to 7 infrared cameras. We place white reflective markers on the subject to capture 3D gesture data. You will now see a video of moving markers placed on the band on the forehead and 2 on the nose. If you observe, there are 4 markers here on the forehead, and if you observe closely, there are 2 more markers on the nose. Similarly, even for this speaker, there are 4 markers on the forehead and 2 more on the nose. Can we identify the speakers just by looking at these 2 sets of markers? Difficult, right? Now, let me play the same video with audio along.
The great king of Krishna Devaraya.
With the audio accompanying the markers, we can easily identify the speaker as the female speaker from our previous video.
So one day, a merchant from a very faraway kingdom, he came to the court.
Now let me play the same video for the second speaker as well.
Well, in the kingdom of
With the help of audio, we can easily identify the speaker as the male speaker from our previous video.
Rama was the wisest. One day, from a foreign kingdom, a merchant comes to the king's court and says, "Your Majesty, I've heard that there are a lot of wise ministers in your court."
Now let me talk about our dataset. From the 3D coordinates which we capture using OptiTrack setup, we calculate Euler angles. Euler angle is basically the angle of deviation from a coordinate axis. We refer the work of Forterar et al. To calculate Euler angles from 3D coordinates. Let us get some more intuition into Euler angles. As we change the angle corresponding to a coordinate axis, the airplane rotates accordingly. This is the summary of the recordings in a database. For a recording, the speakers are given a story and they are instructed to narrate the same story in their impromptu vocabulary. We have a total of 24 speakers with 10 recordings per speaker, 5 recordings in his or her native language and 5 in English, a total of 240 recordings. The longest duration in our database is of 668 seconds duration, while the shortest recording is of 78-second duration. The difference in duration might be due to different speakers explaining at different levels of detail. The mean Euler angle is removed from all the three directions in every recording to remove any recording bias in our dataset. Now, let me talk about the experiments done in this paper. We have an input data with 3 dimensions, each dimension corresponding to the Euler angle corresponding to one of the coordinate axes. To determine the optimal duration to identify speakers, we use different durations of head gestures, which are denoted by WS. So we have an input data point of dimension WS cross 3. The 120 in our architecture represents the sampling rate of our 3D tracking device. We also do a 5-fold cross validation on the entire data set, making sure that every window comes in the test set exactly once. 1D CNN applies the same filter at all the locations, thus capturing local speaker specific features present everywhere. We use F number of 1D CNN filters with padding. As a result, we get an output dimension of WS cross F. Max pooling is applied after 1D CNN to get a single representation for a small kernel of size Ks. As a result, we get an output dimension of floor of WS by Ks cross F. LSTM is meant to capture temporal dependency in a sequence of local features. Global average captures the speaker signature irrespective of the location. Finally, the F dimension vector is passed through a dense layer with softmax activation to get the speaker ID, which is the ID with the highest probability. In our experiments, we have used Adam as the optimizer, cross entropy as the loss function, and a batch size of 10 data points per batch. While identifying speakers, it might happen that user-specific information might not be present in some of the windows while it is present in some other windows, or the speaker-specific information might be dampened in a long duration. So we combine the outputs of multiple windows over a long duration using election mechanism. While combining performance of say P windows, we get the output for each of these P windows by passing it through the model. Then we take the speaker ID, which occurs the maximum number of times in these P windows, as the speaker ID for this set of P windows. Now let's discuss the results we got from our experiments. Here is the TSNE plot for different duration of head gestures. Features are the output of the global average layer in our model before it is fed to the dense layer with softmax activation. As we can see, the speaker-specific clusters indicated by different colors become more and more distinct as we increase the duration of head gestures. This might be due to more speaker-specific information available in head gestures over a longer duration. This graph shows the bar plot of accuracies for the 5 folds in our dataset. We get the highest accuracy for the 70-second window, which is 85.2%. All the window sizes which are statistically similar to the 70-second window are indicated by green dots. We do a Wilcoxon rank test to determine how similar different windows are with respect to the 70-second window. We choose the least window size, after which every window is statistically similar to the 70-second window as our best window. In this case, it turns out to be the 40-second window. This graph shows how the accuracy varies by including more and more windows with single window being 40 seconds in duration. Different colors here indicate different folds in our data with 5 folds for our experiments. As we include more and more windows, the accuracy, as we expect, increases. Location-specific analysis takes into consideration windows starting from both the ends of a recording, that is the beginning and the end. As we can see, as we increase the duration, both the directions, beginning and the end, saturate to the same accuracy. Even in location-independent analysis, where we do not consider the position of analysis but only the duration, we see that the accuracy increases with the duration. This table shows how audio of 3.2 seconds compares with the head gestures of 40-second duration in identifying speakers across the 5 folds of our data using the same network. Though we have almost 37 seconds more of head gestures, the performance with audio is way better than with head gestures. Now let us see what we can conclude from our experiments and results. Some of the key takeaways from our work are: speaker-specific information is encoded in head gesture sequence. Longer the sequence, the better it is for identifying the speakers. Some of the future works we have planned based on this work are to run the model on IE mocap dataset, collect more data for native languages and see if there are any language-specific patterns in head gestures, analyze the correlation between head gestures and speech. These are some of the previous works we have referred for our paper. We thank the Department of Science and Technology, Government of India for their support in this work. Thank you for giving us this opportunity to present at ICASSP 2020. Hope you had some takeaways from this video. Please let us know if you have any questions or suggestions by writing to us at spirelab.ee@iisc.ac.in. Thank you.